Hello everyone, this is Dr. Webb. So in the last video we reviewed exponential functions. In this video we're going to figure out how to take derivatives of them. So let's start off with a simple exponential function. We're going to try and take the derivative of just 2 to the x, right? And so we haven't done any derivatives like this at all, and so all we have right now to fall back on is the definition of derivative, the limit definition. So let's look at that, plug that in. So here's the limit definition we're looking at as the change in x as delta x goes to 0. This is what the limit definition gives us. So looking at this, in the top, we have 2 to the x plus delta x up here minus 2x. And so out of this top here, we can factor out a 2 to the x out of both terms, right? So this 2 to the x plus delta x, we can think about that as being 2 to the x times 2 to the delta x. And then minus 2 to the x, we can think about that as being 2 to the x times 1, which is the same thing as 2 to the 0. I'm going to leave it as 2 to the 0 for how we'll see in a minute. So both of these terms, we can pull out this 2 to the x. And if we do that, we get something that looks like this. Okay, and then this 2 to the x, we can pull this out of the whole limit because it doesn't have any delta x in it anymore. And what we're left with right here, this limit right here, the x is gone. It's only in terms of delta x. So this limit right here doesn't depend on x. In fact, this is the limit we would get specifically if we were trying to find the derivative at 0. So once we pull the 2 to the x out, what's left is, what this means, this derivative here is going to be 2 to the x times the derivative of 2 to the x at x equals 0. So what this means is that if we can figure out what the derivative of 2 to the x just at x equals 0 is, then we're going to know what the derivative is everywhere else just by multiplying by 2 to the x. Okay? So let's try and just look, computationally what that limit's going to be. Let's try and estimate the limit. Okay, so if I plug in 0.1, that's pretty close to 0. Well, you get 0.717. If you get a little bit closer to 0, goes under 0.7, still 0.69555. Get even smaller, gets a little bit smaller, 0.69338. We're doing limit to 0, so we should also check negative things getting close to 0. If we do minus 0.001, we get a little bit less than 6.29. So this limit here is somewhere in between. Limit is probably between these. Okay, so the derivative value of this limit is some number 0.69 something something something. Probably either a 2 or a 3 next. Okay, so that's about as far as we can get with 2. Now if we start with 3 to the x, use the same limit definition, we can do the exact same thing where we pull out a 3 to the x, and we're left again with, this is representing the derivative at x equals 0 of 3 to the x. And so let's see what happens. Let's try and estimate this limit of the derivative 0. And so we plugged in the same values. As you can see, for 3, they're all a bit bigger than 1. And so 0.1, 0.01, it's getting a little bit closer to 1, 0.001, a little bit closer. But then when we do a negative, it gets at 1.098. So that means the real value is somewhere in here, probably. So the value is in between these. Okay, so when we tried to do it with the base 2, we ended up with something that was 0.69. When we plugged it in with the base 3, we ended up with something a little bit bigger than 1. So maybe this means that if there's some number between 2 and 3 where this limit is exactly 1, right? So between 0.69 and 1.09, it's a little bit closer to 3. So let's start trying out other bases and just figuring out this limit and see if we can find some magic number that makes this limit 1. Okay, so we're a little bit closer to 3, so maybe let's start off with 2 3/4. So 2.75, we plug in and estimate this limit. We get that it's 1.01160, so that's closer to 1, but a little bit too big. So let's make it a little bit smaller. Maybe let's try 2.71. Then now it's 0.9969, so that's really close. That's within a little bit more than 3/1000ths. So let's inch that up a little bit higher. Maybe 2.718. Now it's 0.99989, so that's just a little bit more than 1/10,000th away. And so we can keep doing this over and over again, testing out, what the next digit should be, and we end up with this. We can get this infinitely long string of numbers, but it's 2.71828, blah, 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 going on forever. We can keep working it back and forth to get this number that makes the limit exactly 1, right? And so what this means is that if I have an exponential function where this is my base, then that's giving me that the derivative at x equals 0 is exactly 1. Okay, and so that's the nice thing about this number. This limit right here, we're calculating the derivative at x equals 0, and by playing around with the base, we were able to find the number that makes this exactly 1. So I don't want to keep writing out this number, so we should probably give it a name. So, B for base, that's already being used in our general term for base. C's already in the equation for constants. D is in derivative, so we got to pick another letter. So let's pick E. And so we're going to call this number E, and it's the special number, this 2.71828, that makes this limit exactly 1. Okay. And so what this means is that since for exponential functions, the value of the derivative is the exponential function again times this limit. Well, since this limit for e, when e is the base, is equal to 1, that means the derivative is itself. So the derivative of e to the x is e to the x. It is its own derivative. And so then using the rules of exponents, we actually can write any other base, turn it into base e, using the simple rule that any other base b is going to equal e to the natural log of b. And then using this, we now can figure out the derivatives for all exponential functions. Okay, so let's go back to 2 to the x, and we're using this rule, same as before, that 2 is equal to e to the natural log of 2. Then that's raised to the x. Okay, so the rules of exponents then say we can write this as e to the x times natural log of 2. So x times the natural log of 2 is all inside the exponent. Okay, so this natural log of 2 right here, this is a constant. So inside our exponent is x times a constant, and it's raised all to the power e to the x. To work out this derivative, I'm going to think about it as x times natural log of 2 plugged into e to the x. Okay, so to work out the derivative, we're going to be using the chain rule. Our outside function is e to the x. Our inside function is x times the natural log of 2. just as we saw before, what's the derivative of e to the x? It's just e to the x. For the inside, we have that it's x times natural log of 2. Well, that natural log of 2 is just a constant, so it's x times a constant. Derivative of that is the constant. So it's just natural log of 2. And so then what the chain rule says is the derivative of the chain rule is going to give me, it's going to be the derivative of the outside with the inside plugged in times the derivative of the inside. And so that's going to be derivative of the outside with the inside plugged in times derivative of the inside. So e to the x times natural log of 2 times natural log of 2. It would be nice to write this cleanly. Voila. E to the x natural log of 2 times natural log of 2. And then, as we saw before, e to the x natural log of 2, that's the same thing as 2 to the x. E to the x natural log of 2, that's the same thing as 2 to the x. And so we can rewrite it as 2 to the x times natural log of 2. And if you think back about the way that we started this video, that actually means that this number that we got working out that limit, that is the natural log of 2. Okay, so this natural log of 2 right here is the limit as delta x goes to 0 of 2 to the delta x minus 2 to the 0 all over delta x, which is 0.69 blah 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 blah. Okay, and so that means the limit for 3 to the x, the 1 point blah 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 blah, that's actually the natural log of 3. Okay, so especially when we're doing calculus, because e to the x is its own derivative, it is such a nice, wonderful function to take a derivative of, because it is just itself when you take the derivative. Rather than worry about exponential functions in all different bases, anytime that we're going to be wanting to use calculus, it's always going to make the most sense to rewrite it in base e. Right? So we can take any exponential function, c times b to the x, and convert it into c times e to the r to the x. Right? And so really what we're doing here is b is getting swapped out with e to the r. And this r here is going to equal the natural log of b, the same thing that we saw before. So this gives us a new standard form for exponential functions written in base e. So if we want to take the derivative of this, so as we're thinking about this c, this is a constant. So the c is just going to come down. Same as before, taking the derivative of the rest of it, we're going to use the chain rule, where the outside function is e to the x, and then we're plugging into that r times x. And so the derivative of the outside is e to the x. Derivative of the inside, it's a constant times x. So it's that constant r. And so the chain rule says it's going to be derivative of the outside with the inside plugged in times the derivative of the inside. And so that's going to give us derivative of the outside with the inside plugged in is e to the rx again. And then derivative of the outside is just r. And so we can rewrite this as r times c e to the rx. And let's make that look pretty. There it is. And then if you look at this, c times e to the rx, c times e to the rx, same thing again, except now we have this r on the outside. So the value of the derivative here just is the function again times r. So we have f prime of x is equal to r, where r is the coefficient of x inside f of x, times f of x. Well, if I want to solve for r here, say, r is going to be f prime of x divided by f of x. Hopefully that looks familiar. We talked about that a couple weeks ago. This is the relative rate of change. Right? So one way to think about exponential functions are functions where the relative rate of change is a constant. And so in this case, it's r. Okay, so practice problems. So again, for all of these problems, use the fact that if f of x is e to the x, then its derivative is e to the x. So in these problems, you're going to need to play around with this fact using product rule, chain rule, quotient rule, sometimes mixes between them. So try your hand at each of these derivatives, and we will talk about this together Friday morning. See you then. Bye.